For this session, I've chosen to name it the Graph Compression and Distributed Information Processing session. And you can see the titles and authors of the 4 papers there. I'd like to start by introducing the papers on graph compression. So a common question in the area of graph compression has to do with compressing a graph down to a representation that takes a reduced amount of space and allows you to approximately answer distance queries. And such representations are useful for a lot of things. For example, if you're trying to plan a route cross-country and you want to answer questions like, is it faster to go via Chicago or St. Louis? You can either ask Brendan Juba, or you can compute a small space representation of the US road network and hope to use that to obtain accurate answers to most of your questions. A common technique used in this area is something called a graph spanner. This is a subgraph obtained by removing edges from your graph until it is hopefully more sparse, and distances are approximately preserved. And so if you're working on graph spanners, the gold standard, which is usually not achievable, but you hope to get close, is to get down to a linear number of edges. Sublinear obviously makes no sense for this problem, because then you would have isolated vertices, and the distance from such a vertex to any other in the spanner would be infinite. So you sort of don't hope for going below order n. Okay, so this type of representation could compress your graph of the road network down to maybe the number of street intersections in the USA, but not further. And the really innovative idea in this paper is to look at contractions that merge many nodes together into a supernode instead of reducing the size by deleting edges. And if you notice the question that I expressed 2 slides ago, is it faster to go through Chicago or St. Louis? The question already sort of presupposes this notion of graph contraction, because I wasn't asking, for example, is it faster to go from Boston to San Diego by passing through the intersection of Michigan Ave and some street name in Chicago that intersects Michigan, or some other street intersection in St. Louis? So it's evident that the way human beings navigate involves some implicit notion of contraction, and the program committee really appreciated that this paper made that implicit notion explicit in a way that you could actually prove theorems and achieve results that people working in graph spanners might not have thought were possible, like sublinear-sized representations that allow for a certain notion of approximate distance preservation. We have another paper in the session. Again, I'm not going through them in consecutive order, but this will be the 3rd talk, which is also about a different kind of sparsification of graphs. This time not to preserve distances, but to preserve other important parameters of the graph, like the size of a minimum vertex cover or the size of a maximum matching. And the key in this paper is going to be doing this compression in a way that results in a bounded degree graph, and such that the graph, so that all the computations to produce the sparsified graph can be performed locally. In other words, a vertex V, to determine its set of neighbors in the sparsifier, should have to look only at within a small radius of itself, rather than performing some global computation over the entire graph. So these notions evidently connect not only to graph sparsification, but also distributed algorithms. And furthermore, the paper shows that this notion of sparsification has nice applications to dynamic graph algorithms, which is an area that you might not have thought would have anything to do with local algorithms for graph sparsification. The other 2 papers in the session both have to do with different types of information processing in networks. So this one, called Making Asynchronous Distributed Computations Robust to Noise, is about the very basic question of how to communicate over noisy channels. Of course, the seminal work on this question was done by Shannon in 1948, who founded the field of information theory and proved many decisive results on this question as it pertains to one-way communication between two parties. For the question about having an interactive conversation between two parties over a noisy channel, we had to wait almost 50 years for Leonard Schulman's seminal work on coding for interactive communication. This turned out to be a much harder problem to solve because if two parties are having a conversation over a noisy channel, and you thought, Bob thinks that he heard Alice say one thing, but in fact that message got corrupted, it's possible that Bob responds in an inappropriate way, and their entire conversation gets off down a tangent that's irrelevant to executing the protocol that they thought they should be executing, and then you have to have some way of detecting that error and backing it out. Schulman's paper, like Shannon's, launched a series of really important discoveries in interactive communication. Okay, a next series of advances had to do with going beyond two parties. So Rajagopalan and Schulman in 1994 introduced a model of multi-party synchronous communication over a noisy channel that makes random errors. For adversarial errors, actually, the first paper to study this was only very recent, and was in fact in ITCS 3 years ago, that Jane Kalaya and Luco introduced some coding that allows any multi-party synchronous protocol to be simulated under adversarial errors up to some error rate, which is essentially optimal. And the innovation in this paper is that they're able to simulate any multi-party protocol now with asynchronous communication. So I'm not an expert on these matters, but it appears to me that this line of advances, starting with Shannon, has now been pushed to completion, or at least it would be hard for me to think of in what way you would want to generalize this result now that it allows an arbitrary protocol with multi-parties, asynchronous communication, and adversarial errors. I'd also like to advertise that a curious puzzle that is solved in the paper is suppose that we all want to construct a breadth-first search tree among the people attending this conference. And we're going to do it by sending text messages to, each person can send text messages to the people in their address book. But the channel is so noisy that any message you send is going to be replaced by an empty message. Okay, so we have a protocol where we can ping each other, but the ping contains no information apart from the fact that I sent you a message. So the question is, how can we use that communication capability to efficiently find a breadth-first search tree? Okay. The final paper in the session will deal with a very different type of information processing in networks, that is the neural network of the brain, and the way that information in the form of stimuli gets encoded into long-term memories and associations between them. So we all know, for example, that Pavlov did this experiment where every time he presented food to the dog, he rang a bell, the dog salivated. Eventually, the parts of the brain associated with bell ringing and food became associated with each other, and the dog would salivate in response to the bell even if the food were not presented. Or as this cartoonist imagines it, the dog thought he had taught Pavlov to scribble in a notebook every time he drools. That famous experiment demonstrates that these memories and associations form, but says very little about the mechanism by which that happens. A recent experiment reported in 2015 actually gives some insight into the low-level neural mechanisms that lead to the formation and association of these memories. And what the authors of this paper are doing is they're giving a very simple, surprisingly bare-bones mathematical model whereby this low-level mechanism can lead to the formation of stable assemblies of cells, represented in this case as nodes of a GNP graph. The pattern of edge weights in this graph encodes both these stable assemblies that sort of represent long-term memories, and also areas of higher weight connection between two assemblies if the stimuli have been presented together in the past. So a very interesting TCS perspective on a longstanding challenge in neurobiology. All right, so with that, I will turn it over to our first speaker,